Okay, this is section 5.3, multiple access protocols. Um, in one way, we could categorize all links as one of these two. A link is a point-to-point link or it's a broadcast link. A point-to-point link means there's one sender, one receiver on the whole link, okay? That would be something like dial-up access. If you remember that, when you had dial-up access, there was your computer that had a modem, and then there was probably your ISP, like AOL. They had a computer with a modem. You were connected over that modem. Nobody else could talk on that modem. That line between your modem and the AOL's modem, only for you. That makes sense? You don't have to share that 56K with anybody. They're all yours. All right? The other kind of medium is a broadcast medium where you have a shared area, and everybody, multiple people, are sharing that same medium, whether it's a wire or whether it's the air. This is something like in a wireless environment where everybody has to talk in the same room. You could say this is like humans at a party, right? Everybody's talking. That may mean that sometimes you can't hear one conversation because there's the loudmouth behind you who's talking so loudly that you just can't hear the person you'd like to be talking to, right? That's a shared medium. So multiple access protocols solve this problem of how do you share a broadcast channel among multiple senders and receivers in a fair way, hopefully fair. How do you share? All right, so the problem is that there's one channel. If there are two or more simultaneous transmissions, we have a collision. That is, if a node receives two or more signals at the same time, they kind of just garble up each other and he can't distinguish one from the other. Does that make sense?
Simultaneous what?
Simultaneous transmissions. So it's just like if I'm talking to you and Zeke is talking to you at the exact same time, you're probably going to have trouble listening to us both. Yeah? Okay. So that's a collision. A multiple access protocol is an algorithm that allows nodes to share the channel and determine who can transmit when. Okay? Just off the top of your head, can you imagine how do we solve this problem with human beings?
Raise hands.
Raising hands? Okay. Tell me how that works.
If you have a question we all want to answer, we raise our hands and you pick one of us.
Okay, and that would avoid all three of you just blurting out questions at the same time, which might cause me to get noise because those messages collide, in which case I'd have to ask you to retransmit. Yep, so hand raising is one way of doing that. There are other ways as well. I mean, something simple that might happen at a party is if you're polite, you probably don't talk if somebody else is already talking, right? You kind of listen first and then talk. And we'll see how that mechanism is also used in MAC protocols. Okay. These are the four goals that we would like to achieve with a multiple access protocol. Number one, we want it to be efficient. We're going to assume that the maximum speed that nodes can transmit is R bits per second. Okay, so to be efficient, if only one node wants to transmit, then he should be able to transmit at the maximum rate, at R bits per second. Yeah? If you restrict the nodes to less than R and only one node wants to talk, that's a waste of bandwidth, right? So that's what we mean by efficient. Secondly is fair. Let's say we have M nodes that want to transmit. If they all want to transmit, then we want to equally divide the bandwidth among all those M nodes. So that means that they would send at an average rate of R, right, R bits per second, divided by the M nodes that are there. Right? So if we had 10 megabits per second and we had 10 users, the fair thing to do was to let each person transmit at 1 megabit per second. Yeah? It would be unfair if one guy gets 5 and everybody else has to take, the other 5 megabits that are left divided by 9, 5 nights. Fully decentralized is the next goal, the ideal. What that means is we don't want to have to use one node to coordinate everybody. we would like everybody to be able to figure out when they should transmit or not transmit themselves. They don't have to kind of always go through the head node who says, yes, you may talk, you may talk, you may talk. And we're going to see some protocols that do that, but those are kind of bad because then you've got a single point of failure. They're centralized instead of decentralized.
Would you not want just the one point of failure? So that it can only fail in one place rather than it can fail in multiple places? But if it fails there, it fails for everyone.
Right. The fourth thing is simple, and this kind of makes sense. This is a goal, I think, of any algorithm. We would like to be as simple as possible. This is particularly important here because if something is more complex, that means it's going to take more time to do. Or it's going to take more money to do it. If you think about this kind of stuff is typically going to be implemented in hardware. You can make hardware that does complex things, but you have to spend more money to make the hardware. Right? If it takes more circuits to do it, that's more money. So we like to be simple so that it's not expensive or slow. Okay, this is the taxonomy, kind of the classification of MAC protocols. MAC stands for multiple access control. So we're going to look at 3 different broad areas of MAC protocols and then a few examples in each one. Okay, so the first broad area is channel partitioning, and that works by dividing the channel into different pieces. And we could see that we could break it into pieces based on time or based on frequency or even in other ways based on these codes.
Breaking up the time and why?
Breaking up the channel into pieces, which we might do by time slices or by frequency slices. The second class is random access. In this way, we don't divide the channel. Instead, we let whoever wants the channel take the channel and use the whole channel when they want to transmit. The downside to that is collisions are possible. Random access protocols are going to recover from collisions when they occur. So they'll try to reduce the chance of collisions, but they're still possible, and we'll recover from them. In contrast, the channel partitioning protocols, it's impossible for collisions to happen because we've divided it out. So collisions cannot happen, but you only get a piece of the channel when you want to send. The last kind is taking turns, which is when nodes use some mechanism, like the 2 we're going to look at are polling, to only transmit when it's their turn. The complex part there is how does it know when it's their turn? And there's some overhead involved in polling, for instance. In polling, that's kind of the way we might say, okay, Zeke, you talk. All right, Joey, you talk. Lance, you talk. So since we're doing that, I was this authority figure, the authority that was handing out times to talk, and I was the algorithm for determining how the taking turns happened. That means I'm also a single point of failure, kind of bad. All right, let's look at each of these in a little bit more detail. Channel partitioning first. So this means we're dividing the channel into different pieces. TDMA works by dividing it into different time slots. So you can see, in this case, we've divided the time into 6 slots. And you get, say, 1 slot. Each station, each node would get 1 slot. What happens if, in this case, it looks like we've got 6 slots. We could support 6 nodes. What if nodes 2, 5, and 6 don't have anything to send?
You're wasting 3 of the slots.
Right, you're wasting the slots. They just go idle, and that's sort of bad, right? That's a waste. So in this case, we could see that this is very, very fair because you never can exceed R divided by M bits per second, right? It fairly divides the channel, but it's not efficient if only a few of the nodes need to transmit. So that's kind of what's going on there. It is fairly simple. Perhaps it's simple to understand here. What was our third goal? Fully distributed. So this is possibly distributed as long as everybody's clocks are synchronized, then they know when those moments happen. Getting nodes synchronized, though, actually takes some work in actuality, and we're kind of ignoring that. We're glossing over that, but you'd have to do some work to keep them synchronized. FDMA is another channel partitioning method for Mac. It works by breaking the channel into different frequencies, and different nodes transmit at different frequencies. So each station, each node is assigned a fixed frequency. This is kind of like how your radio works, right? Different radio stations transmit at different frequencies, so then you can tune into which ones you want. Yeah. We have the same problem here. What if nodes 2, 5, and 6 don't need to transmit anything? Those frequencies aren't being used, so they're wasted. They go idle. Does this make sense on TDMA and FDMA? We're dividing the channel. They're very fair, but they're not efficient. All right, let's go to the second category, which is the random access protocols. So in this case, when a node has a packet to send, it's going to send it at the full speed of the channel. There's no dividing. It's going to send it full speed, full blast, R bits per second. There's no coordination among the nodes ahead of time. Or they don't agree upon time slices or frequencies. When they want to send something, they send. Collisions are going to happen. We need to be able to detect them and recover from them. Random access protocols define how that happens. So if 2 or more nodes transmit at the same time, there's a collision. The MAC protocol specifies how to detect the collisions, how to recover from the collisions. Typically that's through some sort of delayed retransmission. And we're going to look at several examples of these kinds of MAC protocols: Aloha, slotted Aloha, and some CSMA protocols. CSMA stands for Carrier Sense Multiple Access. Let's start with this slotted Aloha. The assumptions are as follows. We're going to assume that all of the frames are the same size. Every packet is the same size. Okay. Secondly, we're going to assume that time is divided into equal time slots. So we do have the idea of kind of time slots here, but they're not reserved for each individual sender. Anybody can send at any time on any slot, but you always have to start sending your packet at the beginning of a slot. Does that make sense? So we kind of have these frame size time slots. You can only send in the slot. You can't send halfway between 2 slots. You're always going to send in a one whole slot. That's the third point. You only start to transmit at the beginning of a slot. And fourthly, all the nodes can detect a collision. Now, how do you detect a collision? If you hear something other than you are sending, then a collision is happening. Does that make sense? So if you're sending, you need to listen to make sure that what you're sending is what you're hearing. If there's a difference in those two, it means somebody else is also sending and they're messing it up. You can imagine it just at the waves level, right? We're sending waves. Right? When these two waves get combined together, they're going to make it a different waveform than just your waveform, kind of at the physical level. The second column explains the operation of these protocols. What are we going to do? Well, when a node obtains a new frame, so when the network layer passes down a new frame to the link layer, it's going to transmit it. It's going to wait until the next slot happens. When that slot occurs, it'll try to send the packet. If no collision occurs, then it's done, and it can send the next frame in the next slot. If it hears a collision, then it will retransmit the frame in each subsequent slot with this probability P until it's successfully delivered. So let's imagine that P equals 50%. Okay, so we're going to choose 50%. What that means is essentially slotted Aloha works by getting a frame and it tries to send it. If there's a collision, then it's going to flip a coin. Right? If it's heads, it's going to send. It's going to resend the packet on the next frame, the next slot. And if it's tails, it won't send it. and it'll wait till the next time slot, flip the coin again. If it's heads, it'll send it. If it's tails, it won't send it. And it's going to keep doing that, flipping the coin, right, computing the P, until it does send the packet. So you see, the idea here is, right, if you had a collision and two nodes send it at the same time, they both flip the coin. Hopefully one of them gets heads and one of them gets tails. So then only one sends and the other one waits. If they both get heads, what's going to happen? They're both going to send, got another collision, and we're right back to where we were, which is we're going to have to try to resend again. Think about what would happen if we changed that P to some very small number. So P is 10%, so there's a 10% chance that we'll resend. How would that change the situation? Sort of imagine you're rolling a 10-sided die, and if you get a 1, then you get to send. If you get anything else, you have to wait.
Then you might have to wait forever, because you might not never get a 1.
You would probably have to wait longer. You would probably
Yeah.
by probability you should wait longer. What's the other side of that?
You don't want to wait too long.
Right. The good side is you're probably not going to interfere with the other guy. So there's sort of this balancing act, right, by choosing this P, because if you choose a number too big, then you're going to collide again and then just be right back doing it again. If you choose a number too small, you're going to wait unnecessarily long. You kind of feel that tension? But this is how slotted aloha works. I got a visual on this. All right, so let's imagine that we have 3 nodes that all transmit at the same time slice. Okay? So they all try to transmit. They all have a collision. Nobody sends in this next one. So they all roll the dice and decide not to send. 1 and 2 send in this slot. Well, what happens there? Well, that's a collision. That's what these numbers down here, these letters mean. This is collision. This is empty. This is collision. So that was a waste. So we'll have to go back and try again. On this slot, 2 is the only one who sends. So he gets through. That's good. That's success. The next slot ends up being empty. The next slot, 1 and 3 try to go. That's collision. That's bad. The next slot happens to be empty. The next slot, 1 sends by itself. So that's success. And then finally 3 sends. Now, as soon as 2 is successful, he's going to stop trying to send. All right, and likewise, when 1 is successful, he'll stop trying to send. Question?
So confusing.
Is it? What part is confusing? Can you ask a question? And you can imagine each one, the nodes can't see the whole big picture, right? Because it is fully distributed, which is nice. They just know, hey, there was a collision. I need to figure out the probability that I'm going to send next time and either send it or not send it. And if there's a collision, then I'll just keep doing that. Send or not send with some probability. Question?
Okay, so when 1 and 2 has a collision, how is 2 able to send the next slot? But when 1 and 3 has a collision, it has to wait.
All this is just based on probability. So it's just random. It's just chance. It just happens when, at this point, all 3 of them, imagine if it's 50%, all 3 of them flipped the coin and got tails. And nobody sent. In this case, 1 and 2 got heads, 3 got tails. Yeah? In this case, only 2 got heads and was able to send. Does that make sense? So really, all anybody can see is kind of their own, and whether or not there was a collision. They won't even know who they collided with, but just that there was a collision. So the nice thing about slotted aloha is that you can transmit at the full rate if you're the only node that's active, right? If you're one guy who wants to talk, you can just talk. You can blast away full speed. It's highly decentralized. It doesn't require coordination ahead of time. You just have to listen and see if collisions happen and then retransmit later. So it's simple to implement. The cons. Well, whenever there's a collision, we've wasted a slot, and we've wasted a whole slot, right? You've blown the whole thing because actually you see here, you transmit the whole packet, even if there's a collision. You transmit the whole packet. You're going to possibly have idle slots, which is just plain waste. This one is what I was kind of building up to. You see that you might be able to detect that collisions are happening in less than a full slot, but the nodes continue to transmit anyway. That's kind of a waste. This does require clock synchronization in some way because everybody has to know when the slots start, so you know when to go. The reason this is called Aloha, anybody? Would you read this? Is because it was developed at the University of Hawaii, a good place to work, yeah? A good place to go to school. And they were trying to, this was like back in the 70s, they were trying to make a network over multiple islands because they have that issue, right? And so they were doing it over a wireless radio, and this was the protocol they developed. Actually, Aloha was developed first, I believe, and then slotted Aloha. But that's what's called Aloha. It was one of the earliest MAC protocols developed, and it's one of the you could see it as foundational to protocols that come later, like Ethernet. Okay, so Ethernet's kind of like this, but better. One question that we'll often have when we're thinking about these kind of protocols is how efficient are they? How efficient is it for us to send data using this protocol? How many of the slots are successful? And this slide kind of takes you through a mathematical analysis of this to determine what's the average and the best efficiency that we can get. So if we have n nodes that all have a lot of frames to send, and they all want to send at a probability p, all right, then what's the probability that some given node is successful in sending? Right, this is pretty easy. It's the probability that this guy wants to send, p, and everybody else doesn't want to send. Okay, so if we had, that's this 1 minus p is the probability that everyone else doesn't send. All right, you can imagine if p is 20%, yeah, then what we need is we want one node to have a probability of 20%, and everybody else is going to have a probability of 1 minus 20, right, 80%. So that's how we get this n minus 1, that's everybody else, has 80%. The probability that any node has success is this value multiplied times the total number of nodes. Okay. You can analyze this using calculus, right, and find the p star that maximizes this expression by finding the limit of this expression as n goes to infinity. And if you do that, you end up with this value 1 over e. Remember e? Yeah, the base of natural logarithm, which is a value of 0.37. Right? E is what, like 2.2? Cool. All right, so what does this say? This says that the maximum efficiency of slotted Aloha is 30%, 37%. What does that mean? What do you think?
Only 30% of the time it'll work.
It means, at best, the channel is used for useful transmissions 37% of the time.
It's not good.
So what happens to the other 63?
It's either collisions or the slots idle or the nodes idle.
Yeah. So that means if you had a 1 gigabit per second link and you ran slotted Aloha on it, the best speed that you would actually get through would be, what, 370 megabits per second. All that other bandwidth just burns,
That's
disappears.
That's like the maximum. So like you can get less than.
Right, you could get less than that. All right, so this is bad, right? We don't want to waste bandwidth in this way, so let's improve it. let's talk about unslotted aloha for a second. This is simpler. It doesn't require synchronization. The difference is we can send immediately. We don't have to wait for a time slot to start. We can send whenever we're ready. So my question is, if we do this, if we change the rules such that we can send a frame whenever it arrives, does that increase or decrease the probability that collisions occur?
Increase.
Zeke says increase. Joey, what do you think?
What was the question? Sorry.
If we can send a frame whenever it arrives, not just at the beginning of a time slot, but whenever, does that increase or decrease the probability of collisions as compared to slotted aloha? It's coming to you two, Lance. What do you think?
I would think it increase.
You think increase?
Yeah.
What if
I
one's-
jump on it, man.
What if one's sending while another one gets a packet, so they send, so what if they overlap? Like, is that a collision?
What do you think?
It would be, wouldn't it? So
So
it's getting the total bandwidth to send it, and if it starts sending before the other one's finished, then that's a collision.
Yes.
So it would increase it, wouldn't it?
So why? Why does it increase it? Can you state that? Or restate what you were saying?
Well, like, with this kind, you have the full bandwidth, right? And so if you're sending something, a person starts sending it, it doesn't look for a collision. And the person might be almost all the way through, but if they're not completely through with their frame, then it's automatically a collision.
Right. All right. So this is my diagram that I think helps. You're looking at it. The problem is, before, if we had time periods, you could overlap with somebody, but you had to completely overlap or you wouldn't overlap with them at all. Because we've removed the slots, now you can overlap with somebody just 1%. But if you overlap with them 1% of the time, throw it out. It's a whole collision. You've wasted that whole packet, that whole frame. Does that make sense? So it turns out you can run through the same analysis here, and pure Aloha has a maximum efficiency of half slotted Aloha. 18% is the best you can do because there's so much more probability of collisions.
That's the best you can do, or that's the best you can guarantee?
That's
Couldn't it, if it just all happened to work right? I mean, couldn't you just it never overlap?
okay. Well, right.
In the perfect world.
Okay,
But-
I
but
know
that's-
that's well, you don't want to do that because you're
Right.
a chance. But I was just curious if that was possible.
Right. If you're living in this perfect, very improbable world, that's not the world we live in. Maybe, but for practical purposes, if things really are uniformly random, this is what you're going to end up with. Okay, so we have issues with Aloha that we need to fix, and we're going to address a lot of those with CSMA, Carrier Sense Multiple Access. Carrier Sense means I'm going to sense, as in listen, right, to the carrier, where the carrier is the medium, the wire or the air. Basically, those three words sum it up. Listen before you transmit. Listen before you transmit. So when you have a packet to send, you don't just get to send it like you did in Aloha. You're going to listen to the channel first. If the channel is idle, you'll transmit the entire frame. If the channel is busy, then you wait. You defer the transmission. So the human analogy here is don't interrupt other people while they're speaking. If someone's talking, then you definitely shouldn't start talking because you'll definitely interfere with somebody because they're talking right now. Now, does that make sense to you? Listen before you talk. Can collisions still occur? And if so, how? Yes is the right answer, and this diagram explains how. Can you explain that diagram to me? Or can you explain your intuition, Lance, as to how they can still occur? if you think about the human analogy, it might help. Even if you follow the rule, don't talk when other people are talking. Don't start talking when other people are talking. Can two people still talk at the same time?
Yeah, if they both do it right at the same time.
Yeah, right. So if you've had that awkward experience, so people start talking and it's like, oh no, you go ahead. No, you go ahead. Right. That's kind of what's going on. Right. We live in a world that has time and space. So it's possible even that two nodes like B and D might start transmission. They might listen first. They might, well, let's imagine B starts transmitting first at this point in time. Notice time is here, space is here. So all these are apart in space. B starts talking here. D listens at this point, and he can't hear anybody talking because the signal hasn't gotten to him yet. Right? The signal won't get to D until this point in time and space. All right, so likewise, so D starts talking at T1, and B isn't going to hear that until sometime like right here. Does that make sense? How it takes some time for the signal to actually propagate for you to hear that somebody else is talking. So collisions can still occur even though no one was talking when you started. So the propagation delay means that two nodes may not hear each other's transmission. It takes some time for it to get there. Notice in this case, this is under CSMA. Even though we listened before we talked, we transmitted the whole packet and the entire packet was wasted. Both packets were entirely wasted. Yeah? Do note here that the distance between the nodes, which affects the propagation delay, has a major impact on the probability for collisions. Right? If you had a bunch of nodes that were very, very close together, so therefore they could hear each other very, very quickly, they had a very small propagation delay, then the probability for collisions would decrease. Yes? If you're in a system that has high propagation delay, this is going to be an even bigger issue. Okay, so let's improve this again by adding on to CSMA a CD. The CD stands for collision detection. In this case, we're still going to do the carrier sensing and deferral. We're going to wait to send. But now we're going to detect when collisions happen and abort the transmission. We're going to stop sending when we detect a collision. Why do we do that? How does that help?
Because you're going to have to do it anyway. So do it earlier on.
Right, you've got a collision anyway. The collision is going to cause the whole packet to be wasted. There's no point in continuing to prolonging the collision. In this case, you see right here, the checkered area is where the collision is happening. So we would like the collision time to be as small as possible because it's wasted. Yeah. You see on this previous example, we had a lot of checkered because there's a lot of time wasted colliding. The human analogy on this is the polite conversationalist, is what they call it. That just means, right, if we both start talking at the same time, we both stop and let one or the other go. How do you do this? In wired LANs, it's relatively easy to do this. You can measure the signal strengths compared to the transmitted and received signals. You can compare the received signal strengths with the sent signal strengths. If they're the same, then you're the only person talking. Yeah? And if they're not, then you must be getting signals from somebody else. That's a collision. So that's how you physically do the collision detection. In wireless networks, it's difficult because the signal strength attenuates, it decreases so much that if you had one node like yourself, if you're listening to your sent signal strength and you're also receiving signal strength from a distant node, that signal is going to be very weak after all that distance, and you're not going to be able to hear the really distant one over how loudly you're talking. You hear that analogy? Does that make sense? So this CSMA CD doesn't work well in wireless networks. Okay. So does this diagram make sense? There's actually, we need a little bit of time. That's a collision detection abort time. When you detect there's a collision, you have to make sure that you give the other node enough time to detect that there's a collision too. Okay. This is our third big area. This is our last section for MAC protocols, the taking turns protocols. The way this works is well, we're going to kind of see this as possibly a best of both worlds. Notice these properties. The channel partitioning MAC protocols are very efficient and fair at high load. Right? They're always going to be fair, but remember the channel partitioning, if you have a bunch of wasted slots, they're not efficient. If you have a very high load, though, right, if basically everybody always wants to talk, then the channel partitioning will be very efficient. Does that make sense, why that would be the case? If you have low load, it's inefficient. Right? Random access kind of is the opposite scenario. They're efficient at low load. As long as you don't have too many collisions, then people can blast away if they're the only ones who want to talk. And they'll pretty evenly share the channel as long as there's not too much contention. If there's really high load, then you waste a lot of time and bandwidth on collisions. Yeah? And you see up here there cannot be collisions in channel partitioning, so it's nice then that it works at high load. Okay, so you see how these are kind of opposites. We can kind of see taking turns as maybe the best of both worlds, kind of a mixture of the two, or somewhere in between the two. Okay, how do we do this taking turns? One way would be with polling. In this case, we have a master node and these worker nodes. All right, so these worker nodes can only talk if the master node invites them to transmit. And he's going to do it in some turns. So he's going to go say, okay, do you want to talk? Yes, you do. You have data. All right, you send your data to who you want to send it to. Number 2, you want to talk? No? Okay. Number 3, you want to talk? Yes? All right, talk. Number 3, do you want to talk? No. Okay, and back around. So just kind of polling through here, round robin. You see that this is nice because we don't have collisions. And if somebody doesn't want to talk, they don't have to waste bandwidth on them. Right? They don't have a reserved slot that's going idle. We'll just go to the next guy.
Doesn't it take bandwidth to send the invite?
Exactly. And that's exactly what this first one is, the polling overhead. We're wasting bandwidth asking, but that's the way our protocol works. Another issue is there's latency. It takes some time to do that, right? If you're this guy, if you're number 4, and you're the only guy who has to send anything, it doesn't matter. You got to wait for everybody ahead of you in line to say, no, I don't have anything to say, before you even get a chance to send. And so you're going to have to wait that many times. All right, so there's a time issue. And the last one, which I've been kind of making out as the worst, may or may not be, is this single point of failure. Right? What happens to this system if the master node gets turned off? Nobody gets to talk. Right? No one can function if that master node goes down.
Does the data go through the master node?
No. But it doesn't matter, right? The system seems like it could still function if number 1 wants to talk to number 4, but they can't because they're depending on the master node to do the polling. Okay, let's look at perhaps a more elegant way of handling this. Token ring. In this case, you can only talk if you have the token. Right? So imagine we had some physical token here like, this marker, and you can't talk unless you have the marker. Right? So I want to talk, I can talk. All right.
I don't have it.
Z, right?
Uh,
I would really appreciate if we got out of class early.
All right. All right, so I was unable to talk because I didn't have the token, but you could talk if you had it. Does that make sense? If you don't have anything to say, you can pass it along and you don't have to waste that bandwidth. All right, what are the concerns here? There's the token overhead. We're sending around this message, and that takes bandwidth, and it's not usable bandwidth. Maybe it's pretty small, though, so it doesn't matter. We have the same latency issue. That makes sense. Latency. If you're the last guy, if Lance really wants to talk, he can't do it until he gets the token. He's got to wait for everybody else to go through. That would be a bigger issue if there were more people in the network, more nodes in the network. But the third issue here is still the same. Even though we don't have a master node, we have a token, and that's the single point of failure. So you can imagine what would happen if Zeke gets the token and then kind of just drops it. He loses it. He forgets to send it on to the next guy.
But isn't that in the algorithm? So to be a node of the token ring, you have to follow the algorithm. And so you would have to pass it.
Well, you could think about it either way. What if one of these computer systems does have a bug? What if it has the token and then it gets unplugged? That's non-malicious. Then the rest of the network doesn't work because he never sent the message that said, this is the token, I'm done with the token, you take it.
But the same thing works with if a computer doesn't have the token and gets unplugged, because the next node in front of it will send it to it, but if it never receives it.
Okay, so if the ring is broken,
Yeah.
yeah. So we have that issue, some robustness issues either way.
So, like,
But I have a question about the polling. Like, you have the master, and if it goes down, then your
network's down, but what if one of the slaves goes down? Like, does the master send an invite to say slave 2, and if it never gets anything back from slave 2, does it have like a timeout, or does it just sit there and wait till eternity to get something back?
I mean, it would depend on the protocol. This
it
isn't
not
a super specific protocol. This is more of a general approach. I would think they would have a timeout if we were implementing it so that if a node was down, it wouldn't hold up everything, but it would just move to the next.
So, in like theory, would the polling be better than token rating?
I don't know. It's hard to say. They're both not that great, in my opinion.
Because I mean, just thinking about it, like in polling, if your master, if it goes down, then your whole thing's down. But in token ring, if any one of the ones go down, your whole thing's down.
Mm-hmm. I think if you were going to use token ring, you'd have to have some mechanisms in place so that you could always maintain the ring. That is, if a node knew it was going to leave the network, it would have to kind of close the gap and say, okay, now you're connected to this guy. Yeah. Or if you're afraid of just losing a node altogether, you need to maintain the ring. One way I could just think of off the top of my head is if every node knows the next two, this guy and this guy in the ring, then you could recover from one guy going down and close the circle yourself. Make sense? So we could tweak the algorithm to make it more robust, but you still have these issues of overhead, latency, and a single point of failure. I think I have some animation here. Ready for this? Blam. Nothing to send. Send the token on. Oh, he's got data to send. Send the data to whoever it goes to. Wouldn't really be to himself, sorry. Imagine somebody else had gotten it. And then sends the token on. Okay, so this is token passing and polling. Do those things make sense to you? How, from a general level, they're taking turns. Some real protocols that use this, Bluetooth uses it. IBM Token Ring, kind of a dead protocol, I think now, but it used to be that Token Ring and Ethernet were like duking it out to see who would be the standard for network stuff, and you can see who won that. Ethernet definitely came out on top. So we've looked at these three classes of MAC protocols and a few examples in each of how sort of instantiations of those classes. I've spent a lot more time on random access because CSMA CD is used in Ethernet, and we're going to see another version of CSMA collision avoidance, CA, used in 802.11. We'll talk about that in the next chapter, as well as the Aloha protocols. And then we looked at time and frequency division splitting for the channel partitioning. So these are important principles for MAC protocols, and next time we'll look at how addressing is accomplished in the link layer, and also how Ethernet, the details of Ethernet and how it fits into the CSMA CD type of algorithm. Any questions on MAC protocols?